Let's go ahead and get started. Welcome back to ECE 207. There are some dates on the screen which may change. I don't know. It depends on the democracy that we live in, what we actually end up doing. But please make your voice count before you leave today. Put those in the normal location, and maybe halfway through the class somebody can start passing those forward, and we'll end up with 3 collection locations at the end of class, and then I won't have to worry about that. Homework number 4, it doesn't really matter to me whether you turn it in today or on Tuesday. If that would help you, that's fine with me to turn it in, but if we keep delaying things, we'll have to meet on Thanksgiving for our 3rd exam. But that might be an option. You will bring the food, and that will determine your grade. How's that? Today what I want to do is pick up where we left off, actually maybe start a little bit where we had already covered with respect to complex impedances. The reason we are doing this is so that we can essentially solve differential equations using algebra. The algebra that we will use involves complex numbers, but as long as you're comfortable with doing complex algebra, then we can solve differential equations for sinusoidal or AC-driven electrical circuit problems for this class. To do that, we need to develop this concept of a complex impedance, which is analogous to what you've been doing with resistors all along with DC circuits. V is equal to Ri. Now we're going to generalize that to the complex. Instead of having an R, we're going to have a complex impedance Z. And if we convert everything to a complex impedance, now we can treat L's and C's just like R's, except they will each have their own unique complex impedance, and that's what we want to derive today. Once we've derived those relationships for inductors, capacitors, and resistors really remain unchanged. We'll illustrate that concept via an example using AC circuit analysis with those complex impedances that we just derived. We'll then move into power in AC circuit elements, and then we'll talk about complex power. That does not mean complicated, that means complex. We'll have power that's real, we'll have reactive power, which is really the complex component of power, and we'll have the combination of those two, and we'll just call that generic item complex power. Meaning power now will have a real part and an imaginary part. Their complex sum becomes complex power. And it's important to actually know that you might have a reactive component to the power that you're dealing with. Let's now start with this idea of complex impedance. And let me quickly go through the first one that we've really already talked about, and that one was for an inductor. What we're trying to do is derive this complex impedance value or expression for an inductor, and we'll do it by really sort of illustrating it in the time domain. Then we'll go into the complex domain, and hopefully it will be clear what we mean by the complex impedance associated with an inductor. The current, let's say, of this inductor that we're looking at is sine I sub m, that's the magnitude of the current. And then we have sine at a frequency omega t. Because of Eli, we know the current voltage relationship in the time domain of an inductor. V is equal to L di dt. And if we differentiate that sine wave, The L is just a scaling factor, but now that omega comes outside of the argument and scales the result, or scales the voltage, we have L omega cosine omega t plus theta. And where did my I sub m go? Somehow I lost that. That should be remaining. That's also a scaling factor. So we have omega Li times cosine omega t. Let me write it in that form. If we have a sinusoidal current flowing through an inductor, the sinusoidal voltage across that inductor will be related to that current in this relationship. One's a sine and one's a cosine, for example, but the voltage has now been scaled in magnitude by an amount proportional to the frequency of oscillation and proportional to the inductor L. Let's now write those two quantities that are in the time domain, the I sub L of t and the V sub L of t, as phasors. If we do that, the phasor form of I sub L, which, because it's a phasor, has that bar across it, that's going to be some magnitude, I sub m, and its angle. We need to remember that we need to be consistent with the sinusoid. We need to either have all sines or all cosines. Our strategy or policy for this class is let's convert everything to cosines. If we convert that sine to a cosine, then its angle is actually theta minus 90 degrees. Meaning I sub L of t, another way of writing that is I sub m cosine omega t plus theta minus 90 degrees. And now that's the time domain functional expression that we're using to obtain this phasor representation for I sub L. Question?
Did you say that I sub n is the magnitude of the inductor?
No, I hope I didn't. The question was I sub m. I sub m is the magnitude or the amplitude of the sine wave of the current going through the inductor. That's I sub m. I hope I didn't say something other than that. The amplitude of the voltage waveform across the inductor for having its amplitude for the voltage is omega L I sub m. And we can now use that to find the voltage phasor, which is omega L I sub m. Its angle is theta. If we are generalizing these concepts, meaning a resistor, we think of V is equal to Ri. If we generalize that to inductors and capacitors, we want to say, oh, V is equal to Z times I, where Z is this complex impedance. And we want to find this Z for different elements. In this case, we want it to be, I thought I pushed on the red, we want it to be the inductor impedance, and so this would be I sub L and V sub L. We also want to find, if we have, and that will be these phasors, Z sub L in general will be complex. That will be a complex number. If we wanted the capacitor, we want that complex impedance, and we also want the relationship for a resistor. We're trying to now define or identify these different Z's, and hopefully we will find that those Z's are different depending on whether we're dealing with an inductor, a capacitor, or a resistor. I think you can anticipate that Z sub R is actually just going to be the R, because a resistor does not depend on frequency. V is equal to Ri all the time. It's not a differential relationship. Now, what we want to do initially is find this guy, that Z sub L. If this relationship holds, let's now solve that expression for Z sub L and use these phasors for voltage and current that we have already determined exist in terms of they are related to the inductor in that way. Meaning, now we can say that Z sub L is this ratio of the voltage of the inductor divided by the current of the inductor. And we'll use those phasor, we're now going to work in the phasor setting or in the frequency domain. This guy was omega L I sub m at an angle of theta. This was I sub m at an angle of theta minus 90 degrees. Is everybody okay with that? Just taking the ratio, we can cancel some things. What happens when we have angles in the denominator? Do we remember? We subtract them, right? If we had all these angles in the numerator, we would just add those angles. If that's not clear, convert this to exponential form and say, oh, if I had an exponential in the denominator and I want to move it upstairs, that's really like subtracting its exponent. And that's really what we're doing, effectively. Meaning we divide out the magnitudes, which in this case we've already canceled, and we're left with just omega sub L. But now we take the numerator angle and subtract from that the denominator angle. And I should say that's at this angle, so that Z sub L now becomes omega L at an angle of 90 degrees. And that now represents the complex impedance of an inductor. An inductor will basically, its impedance depends on the frequency. Why is that? Well, you have this di dt, and that's a time varying, or it is worried about time variation. That's a derivative. And that's why this omega, which is how fast that current's going anyway, that kind of gives you an idea what's happening. The higher the frequency, the more impedance that inductor is going to present to that current trying to flow. Meaning if you increase the frequency a lot in your signal, that inductor is going to make its resistance more pronounced to that current flowing. It's going to impede it more. And that's what this formula tells us. But we can write this a little differently. If we looked at this phasor relative to the complex plane, here's the real axis, here's the imaginary axis. If I now draw that phasor as a vector in this complex plane, it has a magnitude of length omega L, and what angle does it have? Pi over 2 or 90 degrees, and where is that angle with respect to? To the positive real axis, correct? So I want to go 90 degrees from here, which is just that right angle, and all of my movement or magnitude will be along that direction, and this is now at a length of omega L. And if that's the case, another way of writing 90 degrees could be considered, well, this is now 1 at 90 degrees. If I took that to rectangular form, what would that look like? It's just j, isn't it? Square root of minus 1. We're just going all of it in the imaginary direction, in the positive imaginary direction. So an angle of 90 degrees, you could say that's also equal to j. Meaning, instead of writing Z sub L as omega L at 90 degrees, you might see it written the following. You might say, oh, my inductor impedance is actually Z sub L equal J omega L.
What does it mean for the impedance to be imaginary?
So now what does it mean for the question was, what does it mean for the impedance to be imaginary? This is now an ideal inductor. And an ideal inductor is just this coil of wire, and ideally it does not have any resistance. Meaning, all it's doing is storing energy in the magnetic field around that coil. And if you're operating this with a sine wave, that sine wave goes positive, negative, positive, negative, positive, negative. It's going to actually energize that magnetic field and then collapse the magnetic field. Energize, collapse. And when it collapses, what's it doing? It's throwing that power, if you think of the power of that inductor, that power now is getting returned to the circuit. It builds it up, takes it in, and then it goes away. Takes it in, goes away. It's really not doing any real work. That's why it's all imaginary. Okay? So it's building up and giving back. Building up, giving back. And it does it. Everything it takes on, it gives back. If it's ideal, there's no resistance. In real systems, there is some resistance in that wire or coil, so you would represent an inductor, a real inductor, as having a little resistance plus J omega L if you were analyzing it in sinusoidal steady state. Other questions? Question?
This goes way back. I think you just answered the question. The induct IL of T, we're writing as Im sine because it's sinusoidal current that we normally deal with, or we have the standard current is sinusoidal, right?
Okay, the question was, I defined I sub L as I sub M sine omega t plus theta. I just wanted it to be a sine wave. I just wanted it to be sinusoidal, but I knew that Eli existed, and I was going to have to take the derivative of whatever I defined I to be. I said, I don't want to deal with negative signs, so I know the derivative of a sine is cosine. No negative involved. That's why I selected arbitrarily to begin this discussion with I sub L having a current that was a sine, S-I-N-E signal. That's the only reason that is selected that way, or for that reason. But now that I selected it, I had to live with that selection. Living with that selection gave me a cosine for the voltage, meaning the current and the voltage are how far apart? Pi over 2. Which one is where? Does that make any sense? Which one is where? How are the current and voltage related in this inductor? If I said, is the current behind or ahead of the voltage, what would you say? The current is behind or it lags the voltage. Do you see that? Because what's the angle? The voltage angle is theta. The current angle is exactly 90 degrees behind that. It's theta minus 90 degrees. The current lags the voltage in this inductor. And that actually is said here because we know that V sub L is equal to Z sub L I sub L. And what does that Z sub L do? It catches it up. So that Z sub L times I sub L is actually going to make the voltage 90 degrees ahead of the current because we have that J, that pure imaginary piece, in our impedance for the inductor. Meaning Eli, or however you want to think of it, you now know that the current lags the voltage in an inductor. Questions on that derivation? We've now derived this relationship for the complex impedance. This is a generalization of resistors. Now we know we're working with sinusoidally excited circuits. We have sine waves. That's all that's exciting our system. And with that, we can now describe this impedance of an inductor by this complex quantity. And in particular, it's J omega L. Question?
Are we supposed to have the bar above V sub L and I sub
Are we supposed to have the bar above Z sub L?
V sub L and I sub L?
Oh, gosh, you guys and your bars. Put it behind bars, okay? Yes, it should be barred.
Okay.
If it's going to be complex or a phasor, the question was, do we want bars on top of V sub L and I sub L? Yes, is the answer. I'm going to probably get sloppy. But that means that we have V sub L in general is a magnitude and an angle. I sub L is a magnitude and an angle. They're related to each other by Z sub L, the impedance of that inductor. Other questions or concerns about what I am or am not doing? Okay, some of you may have seen me going away from this classroom today before class started. I was not running away, but going out of the union, I noticed something on my shirt, and I did that, and it just smeared everywhere. It was a bird, something. And I wasn't going to let a bird ruin my day, so I cleaned up before class. But I'm still wet. I'll have to clean it up a little bit better later, but hopefully now you're not getting, oh, when you look at me. Hopefully you're taking notes frantically. I don't even know why I said that. I didn't have to admit it, but some of you are going, where are you going? Nowhere. All right, capacitor. Let's do the same thing for capacitors. V sub C of t. And now you're going to wonder, why did I start with V? Well, now I think you can guess why I start with V. And I'm going to make that V sub m sine of omega t plus theta. All I'm really trying to do is derive a relationship between voltage and current on a capacitor to find its complex impedance. And I can start with whatever I want. I just have to keep consistent once I've selected my starting point. My starting point now is V sub m sine of omega t plus theta. If that's the case, by ice, I know that I sub c is c dV sub c of t dt. If I take the derivative of that sine, I now have omega c V sub m cosine omega t plus theta. That's now how my current is related to my voltage in the time domain for a capacitor. And that's just ice. If we now do exactly the same steps that we did before, and I'll put the bar over it, we now want to go into the frequency domain. We're running over here, right? We're now in the frequency domain. And you need to remember where you're at. You're either in the time domain or frequency domain. And why are we going to the frequency domain? So we can do algebra instead of differential equations. Yes. Woo! V sub c. That's V sub m at an angle of theta. I sub c in phasor form is now omega c V sub m at an angle. Oh, what am I doing? Can you guys wake me up? That was a sine, wasn't it? Not an S-I-G-N, but an S-I-N-E. That was the sine. We need to convert it to a cosine for voltage. So that's now theta minus 90. I sub c, phasor form, has an angle of theta. Are we still okay relative to errors or no errors? Good. I like to see thumbs. Okay? That was 2 thumbs up if you're watching. or 1, it doesn't matter. 1's okay. Z sub C. That again, we're looking for this ratio of voltage over current to give us what the complex impedance is going to be. This is V sub C bar over I sub C bar. We now have V sub M at an angle of theta minus 90 degrees over omega C V sub M at an angle of theta. We subtract, well, let's cancel. We can cancel the common magnitude of V sub M. We now have 1 over omega C at what angle? Minus 90 degrees. And now this minus 90 degrees, if you're looking in the complex plane, that's minus J, isn't it? We're now down below the real axis by minus 90. That's actually going in the imaginary direction, all in the imaginary axis, and so our scaling factor is minus J. We may not want to keep track of minus signs, so let's just multiply by 1, and we now have minus J times J over J, 3 J's. That was probably a J that ended up on my shoulder. Sorry. A blue jay. Oh, it's blue. We have three blue jays. Okay? What does that almost looks like a face on the right. If you're in the audience, I'm usually not. I'm buried in my screen. What are JJ? What's JJ? J squared, that's minus 1. That cancels the negative. So we can rewrite minus J as 1 over J, or we can rewrite minus 90 degrees as 1 over J. Now that allows us to combine all of our variables down in the basement of our impedance for Z sub C. That's equivalent to 1 over omega C at an angle of minus 90 degrees. Is that making any sense? So we now have our capacitor impedance. Available. That's Z sub C. That's 1 over omega C at an angle of minus 90 degrees, or it's 1 over J omega C. And that you'll put on your crib sheet for the exam. You'll say, oh, if I'm dealing with sinusoidal steady state analysis, I'm going to use that complex impedance, Z sub C, for my capacitors. How are the current and the voltage related in this capacitor? What do we want to say about the current in a capacitor? It leads the voltage, doesn't it? So now we have ice. So and you might say, why am I using ice? Well, which one is in front of the other? Ice is in front of E. Ice leads the voltage in a capacitor. So we could say that the current, and you saw that from the phasor angles, the current leads the voltage in a capacitor. And if we were doing Eli, I is behind the E, isn't it? So I lags the voltage in this inductor, in an inductor. Questions on complex impedances for capacitors and inductors? This one now is reciprocally related to the inductor, meaning those two can be used to cancel each other out. Bless you. Question?
Okay, so when you say current leads voltage or vice versa, is that something that you can physically see or like experience on or measure or something?
The question is, can we experience this current leading the voltage? Can we all close our eyes, breathe deep? Your eyes are not closed. Can we experience this? I'm going to try to show you something when we get into power. I wasn't going to do that just yet, but now that you've asked, I'll go ahead and get ahead of myself. Here are the voltage current relationships for capacitors and inductors. You don't have to look at the bottom one, but the reason I'm showing it is because that's where the legend is. But the right is capacitors, on the left is inductors. The black curve, I believe, in both is voltage. The blue is current. Meaning, what did we just say? Current is behind voltage in an inductor. On the left side, if we look at that, which one is peaking first? And remember, first is smaller values of time. So as we're walking to the right on that time axis, which one peaks first? The black curve, which is voltage. I hope this is consistent with what we said. I lags. So voltage leads current in an inductor. Eli. So the black voltage waveform is 90 degrees ahead in an inductor of the blue current. Does that make sense? So that's 90 degrees in angle, but in time that's going to depend on the frequency. We're not going to worry about that, but you can see that the voltage is peaking before the current is peaking. Conversely, if we look at the capacitor, what's happening? Now let's go over to sort of the first peak that we see, and the blue is peaking before the voltage. So the current leads the voltage in the capacitor. And that's how we experience voltage and current leading and lagging in inductors and currents, or in inductors and capacitors. I got too much into the experience. Does that help? You can always graph these, or, whoa, now I've lost. That's why you did that question. You wanted me to get completely lost. I got too into this experience. Other questions? But that particular figure was figure 522 in the 4th edition of Hambly. If you're following along, if you're reading, if you open up your book, please open up your book today to page, I don't know what page number that's on. It's not important. But it is figure, I believe, 522. Let's look at resistance. Voltage of a resistor. How do I want to say this? Maybe I should have started with current. Well, it doesn't really matter, does it? Current, I of t in an I sub r, let's say is I sub m cosine omega t plus theta. What's the voltage current relationship of a resistor? That's Ohm's law, isn't it? Ri. So this is now R times I sub r of t, or this is now R I sub m cosine omega t plus theta. If we wanted the phasor for the voltage, that's the magnitude of that cosine waveform, which is R times I sub m at the angle of theta. The phasor form of the current is I sub m at an angle theta. What's the impedance? R. You're way ahead of me. But if we went and derived it based on these phasor relationships for voltage and current, this is V sub R over I sub R with bars. This is now R I sub M at an angle of theta, and this is I sub M at an angle of theta. Now we can just get crazy with how we can clean that up, and that just becomes R. We have theta minus theta. You could say, and now that is not theta or phi, that's 0, isn't it? That shouldn't have a line going horizontally or vertically in it. That's a 0. This is now R. So it's not even complex. And what do we know about the voltage and the current relative to each other? Does one lead the other? No. They are what's called in phase. They line up. Their peaks line up. If you looked at the peak of the current, peak of the voltage, they're always right on top of each other. So the voltage and current are in phase. In a resistor. And that's the current voltage relationship right there of voltage and current on a resistor. Those waveforms are lined up. They aren't necessarily at the same magnitude, are they? Because they differ by the resistance R. R scales the voltage, R scales the current to give you voltage, depending on what R is. Questions on that? Now we have all of these complex impedances that we need to analyze a circuit. And why don't we just open up our textbooks and do some circuit analysis? And in particular, let's work one of these problems that's in the book. Let's work problem 52 in chapter 5. And I don't even have that problem. All I have is the circuit. Here's the circuit. It has an inductor, has a resistor, it has a capacitor. And my voltage source is 100 cosine of 10 to the 4th t. This is 10 millihenries. This is 100 ohms. And this is 1 microfarad. Now, did somebody actually open up their book kindly enough for me? And I can maybe try to read? That's scary. Oh, I need to define some currents. So it says in this problem, find the phasors I, where I is bold. It doesn't have a bar, but I can't bold on my tablet, so I bar. Is that okay? So the reason I bar is because I can't bold. Is that okay? So we need to find the phasors for I sub R, and I sub C, and I need to define those, but those are fairly clear what those are. Here is I. Here is I sub R, and there's I sub C. But we want to find those in phasor form. But that's now a circuit in the time domain, isn't it? We have a source that's oscillating. What's the frequency of oscillation? That's omega, isn't it? It's in radians per second. And that's 10,000 radians per second. Does everybody know what that is in hertz? Divide it by 2 pi. That's all you have to do. If somebody said, well, I wanted the frequency in hertz, well, you can give them the frequency in hertz if they really wanted it. Omega is 2 pi f. You can always remember that, or it's 2 pi over cap t. And you could find the period. If somebody said, can you sketch this waveform for me? You can say, sure, I can sketch this waveform. You have a napkin? So when you're enjoying a cup of coffee or something, you can pull out your napkin and draw this circuit and analyze it. And then you'll really enjoy your coffee. Okay? Where was I? Oh, I need to find these red currents, but I need to find their phasor forms. What's the impedance? So now I'm going to redraw that circuit in the frequency domain, in the complex domain. And to do that, I need to now identify the complex impedances for the inductor, resistor, and capacitor. Oh, that's what I knew. I scrolled up for a reason. We didn't solve this in Chapter 4, did we? What's the order of this circuit? Second order. We have 2 energy storage elements in that, and we didn't solve any of those. We didn't solve any second order differential equations. We could, but I assume you've had 254, and so we'll just worry about doing higher order circuits in the frequency domain with sinusoidal analysis. And I'm sure I will not get too many objections. Or do you want a 10th order differential equation on the second exam? Yes? Okay. Just for you. And your classmates will thank you for that. And I'll see your name and face in the Wildcat tomorrow. We will go to your funeral. What's Z sub R? R. What was R? That was 100. What's Z sub L? We just defined that to be J omega L. That's going to be a complex quantity. And that's why we had to pull out omega. That omega is on the side of our napkin. That's now 10 to the 4th. That we have to use to define these Z's. We now have J times 10 to the 4th. And what was L? 10 millihenries. So that was 10 times 10 to the minus 3. So what's our exponent on 10? We have 10 to the minus 2 and 10 to the 4th. Z sub L is now J100 as a complex quantity. What about Z sub C? That's this 1 over J omega C. C was 1 microfarad, which is 1 times 10 to the minus 6. That's now, I'm going to pull the J upstairs. I can do that by multiplying or flipping it if that's what you want to do, but remember you have to change the sign if you do that, or you can multiply by J over J. 3 J's again, now they're black, so we won't do that. But this is now 10 to the minus 2 in the basement, or 100 if we pull that upstairs. And so now the impedance of our capacitor is minus J100. Now we can go into the frequency domain. Everybody see that? We now have these complex values, these complex numbers that will allow us to move from the time domain into the frequency domain. We can now resketch that circuit. Structurally, we do not change any locations or connections of the circuit. We keep it the same. Our inductor was there. Here was our resistor. Here was our capacitor. And what do? This now is J100. That's its impedance. The impedance of the resistor was 100. The impedance of the capacitor was minus J100. What's our input? What's our voltage source? We now go from time domain into the frequency domain, which means we take the time domain expression and convert it to a phasor. What's the phasor representation of our original voltage? What was the amplitude of that sinusoid? 100. What was its angle? That's now our source. If that was 100 cosine omega t plus 30 degrees, we'd need to have an angle of 30 degrees. And the omega we need to keep track of, but now it's just on the side of our paper. You do not see omega anywhere in that circuit. It's buried in the values of the impedances. Those are frequency-dependent quantities. If somebody changes the supply voltage to a different frequency, that inductor and capacitor are going to look different in terms of their values of their impedance. One will still be plus J, one will still be minus J, but the magnitudes will be different because they depend on omega, the frequency. What were we asked to find? We needed I think that was this, wasn't it? And that will have a bar over it. I sub R with a bar, I sub C with a bar. And I've been noticing that you guys, as a class, get a little bit nervous when things are put on a circuit. Meaning, if I now defined something, you don't have to live with those. You could erase those, either physically or virtually. You don't have to keep those there if that's going to mess you up for solving it. I'm just seeing if it looks the same up here as it does down below. Actually, I need to do an eye exam, eye test. No, not really. I just need to wake up, so I'm walking around. I'm sorry. You guys don't get that, so I feel your pain. You cannot get up and move around. I kind of have you as a captive audience, huh? Oh, was that a question? I was going to exercise. Oh, in a wave? Okay, what?
I think I'm about to learn something, so I'm excited.
So am I, but the restroom, we have to wait.
Just sort of slowly go back over okay, so we've got this circuit. We don't have a DC current anymore. We've got this sinusoidal current, so now we have these elements that have an impedance, right?
Yes.
Which is also sinusoidal. But normally we just model that by a differential equation. We don't want to do that. We want to go into the frequency domain and analyze this stuff with multiplying phasors. So can you just sort of explain? I mean, is that, am I on track here?
You just gave my lecture in a minute. I can just leave, and you guys... Did everybody hear that lecture?
Yes.
I'm supposed to repeat it for the benefit of the tablet.
We can do that because
We can do that because we know what's going to happen. We can anticipate. So the question was, how did we go, or why did we go from this time domain circuit and somehow go down to the frequency domain? We did that because what did we learn in Chapter 4? We know from Chapter 4 that if we excite our circuit with a forcing function, typically all the currents and voltages are going to look like that forcing function after the transient. What influences the transient? Well, that is influenced by the way this circuit is built and the resistance. But if we have resistors in there, we're going to have transients that will decay. And they'll probably decay pretty quickly in an electrical circuit. After 5 time constants, we've basically reached steady state. And if we're shaking this with a sine wave, that's not recorded, luckily. Now I've lost track. We're shaking this sinusoidally. Because we're doing that, we can now analyze or think about what's happening with all of these currents and voltages. We know that they are shaking or moving at exactly that same frequency because this is a linear circuit. We know the current and voltages on these capacitors and inductors remain at that same frequency. That's why we sort of pulled that omega to the side and put it on our napkin, and it's buried now in our phasor relationship. But it did influence, because of what we just derived earlier with respect to our complex impedances, we now know how to relate that frequency and the L's and the C's and the R's to these new quantities that are now in the frequency domain. Now we're ready to solve this, and if we can solve this, we can, at the end, go back into the time domain, because somebody's going to say, I have no idea why you're playing in the frequency domain. Can you just tell me what the voltage is or what the current is? And you can say, I sure can. Because you can move from the frequency domain back into the time domain, but it's a lot easier to play with algebra than differential equations. And that's why we're able to do this. We know the transients are going to go away. We're going to be in sinusoidal steady state after 5 time constants, which isn't going to take very long, and now we can just play with sines and cosine. That's why we're able to do what we're doing, because we're saying we're going to forget the transient and just look at the sinusoidal steady state behavior of this circuit. I wish I could throw a curveball, and I wish I was left-handed, but I'm sorry. On the exam, I might throw a curveball, but I don't think I won't be throwing it relative to sinusoidal steady state. I may give you a transient problem that you may say, well, where did that come from? But that's Chapter 4 material. Other questions? Are we ready to analyze this? Oh, I started walking up the stairs reminding myself that those red currents, if that's making you feel uncomfortable or nervous, just erase them and solve this however you want to solve it. How would you like to solve this problem? Mesh? I don't know why we like mesh, but that's what we like. I liked mesh too if I was in your position. But how many mesh currents do we have if we solved it with mesh? 2. How many node voltages do we have if we solve it with nodal analysis? 1. Do you want to have 2 equations or 1 equation? See? You guys have learned how to analyze these circuits. You can do that on the exam. You can say, look, this looks like a mesh problem, but let me just wait just a minute. If I did that with nodal analysis, I'd only have 1 equation, 1 unknown, and I could be done. Did everybody see that? Where is our node that we want to define? There's a common node, isn't it? We also have this node, but that's already defined. That's given. That's given to us as 100 at an angle of 0. And if we can find this node voltage, let's call it V sub 1, we can actually find all of these currents that we want, because we could then find that current once we found I sub R and I sub C. Questions on that decision? Question?
So there is 2 nodes, or there's only 1 node?
Oh, there's a lot of nodes, aren't there? The question was, is there 1 node, 2 nodes? So I should have said, how many unknown nodes are there, or how many nodes do we have to find in order to find everything we need to know about in this circuit? And that's really only that 1 node that I've circled with dashed lines. There are 3 nodes in this problem, aren't there? There's the bottom one, but that's the one we're going to call our reference node. There's the one above the voltage source, but we know what that is. That's always at 100 at 0 degrees. That's a source, and we can define that. The only unknown is the one that we've labeled as V sub 1, and that will be a phasor quantity because we have complex impedances. We have inductors and capacitors. Questions on that? Those are good questions. I'm being a little bit quick on my saying, oh, there's only one node. There's really more nodes than one, but there's one that we really want to find, is maybe a better way of saying it. If we write KCL at that node, now you can forget that blue eye, because I maybe want to look at all of the currents going out of that node and sum those and set those equal to 0. KCL still holds when we're dealing with complex numbers. If I want to know the current going from the node that we've circled to the source node, I want to go from right to left with a positive current through that inductor, how would I define it? Exactly the way you've defined currents this semester. It would be that rightmost current or node that we've defined, V sub 1, minus this 100, and divide it by the impedance, J100. That will give us the current positive going in the left direction. If it turns out it's not positive, well, that just means that it's coming into the node. That's okay. Signs will take care of themselves. But we now can say that we have V1 minus 100 at 0 degrees over J100. Everybody okay with where that came from? Now we're treating all these complex impedances like they were just general resistors. Question? Where did that come from? How do I say this differently? If we climb up to the potential of V1 and we look to the left and look to the source, I'm now assuming that I'm going basically downhill in altitude. And I want to know what's going to make that current go down in altitude. Then I'm going to say where I'm at up high, V1 minus the 100, that's going to give me the voltage dropped across that impedance. And I now need to divide by that impedance, which is J100. If that doesn't make sense, replace all these inductors and capacitors with resistors and just see if you can make it make sense with resistors, and then say, now my L's and C's are generalized resistors. Let me put them in. Now they're complex numbers. Question? This current that I've defined now is actually going to the left. That's a positive current going from right to left. So that is not this guy. It is this current. Do I have an I1 anywhere? This is I1. Is that okay? What is the current going down through the resistor? That's now coming out of the node going down. That I'm going to say is V1 over the R, which is just 100. What's the current going out of the far right or coming down through the far right branch? V1 over this complex impedance, which is just minus J100. And what do we know about KCL? Those are all the currents out of that node. They need to sum to 0. Questions on that equation? That's one equation and one unknown, and if we can find that one unknown, which is V sub 1 bar, meaning it's complex, then we will be able to derive all of these other quantities that we want. I bar, I sub R bar, I sub C bar. We'll be able to find those once we've determined or solved for V sub 1 bar. And V sub 1 bar might be complex. That's okay. Questions? That's why you bought that expensive calculator, so you could solve complex problems with it.
Why doesn't the first,
I'm sorry?
why isn't the first term the negative of this second term?
Why is the first term?
Like why, I mean, since
Oh, you redefined
that's
it.
going into the node and the other two.
No, you redefined it.
I redefined it. The current that I have, well, I now have V1 bar minus 100, so that's now I'm saying I want to know what current is going to the left out of that node, and that's leaving the node.
Oh, okay.
So V1, where am I right now? That's V1. Where am I going to in potential is 100. So I take V1 minus where I'm going. V1 minus 100. All these other V1s, I'm referencing those to the reference node, which is 0. So that's V1 minus 0 over 100, V1 bar over minus 0 over minus J100. Other questions? Now we just have to do the algebra. Let's collect all the coefficients that scale or multiply V sub 1 bar. Meaning, I can now say I have a 1 over J100, I have a 100, and I have a 1 over minus J100. Those are all scaling V sub 1, and I'm going to pull this piece and move that to the other side. And when I do that, that minus sign is gone, and I have 100 at 0 degrees all over J100. Questions on that? Whoops. This and that cancel. I'm just going to do algebra, and I now have 1 over 100 V sub 1 bar is equal to these hundreds, if I want, go away, 0 degrees over 90 degrees, or this is now minus 90 degrees, or that's minus J. You could write it however you want to write it. But I might write it as an angle of minus 90, so that now V1, I can scale both sides or multiply both sides by 100, and that gives me V1 bar on the left is equal to 100 at minus 90 degrees. Questions on that? Question.
Can we leave it as 100 minus J? 100 negative J?
Can we leave it as 100 minus J? Yes, you can. But I'm going to now start finding currents, and so I want to have that V in a polar form. I mean, just having an imaginary quantity, that's just one number, but it's 0 minus J if you thought of it as rectangular form. And to do multiplication or division, it's cleaner or easier to just convert everything to polar coordinates and play in polar coordinates. So I want a magnitude and an angle, just to make it easier. I want to now find my currents of interest. One of those was I sub R bar. How is that related to V1? I sub R is just the current going down in that resistor. V1 is the voltage dropped across that resistor, meaning I should just have to divide that V1 by R. In this case, I have 100 at minus 90 degrees divided by 100, or I now have 1 at minus 90 degrees. And we can now go into the time domain if we want, but let's do all of these at once. But you now know that that current in the resistor lags the original supply voltage by 90 degrees because the original supply voltage started at 0 degrees. And now this one relative to that is minus 90. What about I sub C? That's just V divided by Z, where Z is the impedance, complex impedance of that capacitor. This was 100 at minus 90, but what was our capacitor's impedance? That was minus J 100, wasn't it? And what is minus J? That's actually just minus 90. And if you want to explicitly keep track of that angle, that's now 1 at 0 degrees. That's saying that capacitor current has a magnitude of 1 and it's in phase with the supply voltage because it's not in parallel with that, or it's interconnected, and that's why it can actually be in phase, because there's an inductor in that circuit as well as a resistor. And in this case, the resistor current is 90 degrees behind the supply voltage. Question?
All in the real direction?
I'm sorry?
By 0 degrees, it's all.
0 degrees, all of these angles, we are referring all of these angles to the positive real axis. So we started our voltage that we were given started at 0 degrees. And now we're finding everything relative to that particular voltage reference phase. I was now the current going into that node that we solved for. If we go back, I don't know if we're going to find it. Did I erase it? This, now what I want is I actually want this guy, and I could do KCL at that node and say that I bar is equal to I sub R plus I sub C. So this guy is now I sub R plus I sub C, and I have both of those. I have this one is 1 at minus 90. I have the other one as 1 at 0 degrees. And if I'm adding things, it might be helpful to go to rectangular coordinates. What's 1 at minus 90? What's the real part? So now if you lose track, you can say, well, that minus 90, I could do Euler's with that. And so that would be cosine of minus 90 plus j sine of minus 90. What's the cosine of minus 90? What's the cosine of 90? What's the cosine of pi over 2? 0. So this is now 0 minus j, isn't it? That's the first piece taken into the rectangular form. And what's the next piece? 1 at 0 degrees. Isn't that this? 1 is 1. Or I now have, this is 1 minus j. That's I. And what is 1 minus j if I wanted to find that in polar form? If it's not making too much sense, I would just sketch it. Here's 1, and here's minus j. And I'm now adding those up, meaning now that vector, I, is right there. And now I have a right triangle with one side being 1, the other side being 1, and I'm really looking for the hypotenuse of that right triangle. And the angle relative to the real axis is right there. Or you could say, you know what, I have no idea what he's talking about. Well, it's real part squared plus imaginary part squared at an angle of the inverse tangent of the imaginary part over the real part. That's the square root of 2 at an angle. What's the angle that has a tangent of -1? And isn't that what this is? This is 45 degrees in the negative direction, and this distance or length, if I have 1s on both sides of my right triangle, its hypotenuse is the square root of 2. That's I. Where are my I sub r's and I sub c's? If I drew those in this complex plane, graphically then, how are my currents related? Where is I sub c? So this one was here, and I sub c was right here, wasn't it? I don't need to scroll up anymore. Let me just highlight it. Here is I sub c. Wasn't that I sub c? And let me just, I feel like coloring. Here is I sub r. Yes? And now we can put those on the axis. Here is which one? That's I sub c. And where's I sub r? Questions on that?
You also found I using the impedance of the inductor.
Could I have found I using the impedance of the inductor? Yes, you could have, going from V1 bar minus 100 divided by the impedance of the inductor. But in this case, we wanted it to go from left to right, so it would have been 100 minus V1 bar over J100.
Can you change the order like that even though
Yes, you can change the order. You can do whatever you want once you know the relationships. Hey, 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 hey. Wait. Did I get your votes passed to the appropriate direction? And let's go in. Before you leave, I can't leave you in the complex plane. Before you go out these doors, you have to be in the time domain. I can't leave. You'll be messed up all weekend. So what's I sub r? What is that in the time domain?
1 cosine omega t minus 90 degrees.
Does everybody see that? An omega is 10 to the 4th. Now we pull it off of our napkin. And that's coming because we know the angle is minus 90. We know the magnitude is 1. What about I sub c? Its magnitude was 1. It's oscillating at exactly the same omega. What's its angle? It didn't have an angle. You wouldn't have even had to put that plus 0. You could have just said 10 to the 4th t. What's the current I of t, which is really the inductor current going from left to right? That's I. What's its magnitude? Square root of 2. It's still a cosine at the same frequency. What's its angle? And now you can go home and experience those currents. You can draw those and see where they peak. Have a good weekend, and I'll see you on Tuesday.